In this video, we're going to look at two more chi-square tests for analyzing categorical data. In the last video, we looked at a goodness of fit test, and in this video, we're going to do a test of independence and a test of homogeneity. So we'll start with the test of independence. Now, in this test, the claims are about the independence of two methods of classification. So what we do is we take an observation or a sample from one population and we classify each subject in the sample in two ways of classification. So for example, we can classify each subject by gender as well as opinion on some political issue. Or we can look at whether or not a subject has received a flu shot or two flu shots or no flu shot, and then we could classify them as whether or not they actually got the flu. So again, we look at a single sample from one population and we classify each subject in two ways. And the claim is that these two methods of classification are independent. Okay, so as what we're going to do is we're going to look at contingency tables in a moment, and that's how we actually organize or summarize our sample data. Our null hypothesis is always that the row variable, or one of the methods of classification, is independent of the column variable, which is another way of classification. Okay. So another way to say that is that the row and column variables are independent of one another. And of course the alternative is that they are not independent of one another. So we can say the row variable is dependent on the column variable, or we can say that the row and column variables are dependent on one another. Now the rejection region, as in the goodness of fit test, is always right-tailed. Okay. But the degrees of freedom is calculated a little differently. The degrees of freedom is given by r minus 1 multiplied by c minus 1. Okay, now r here is the number of rows we have. In other words, the number of possible classes that the first method of classification has, and c is the number of columns, or the number of classes that the second method of classification has. Okay. The test statistic is, again, in form very similar to the goodness of fit test. We see how far the observed counts are from what the expected counts are, and we add that up over all the cells, or all the two classifications. Okay, so let's look at this a little more detail. So a contingency table, or a dependency table, basically lists the counts of our sample with respect to two methods of classification. Of course, we're going to call these the row variable and the column variable. Now here's a more specific example. Okay, so here consider a plant that manufactures furniture. Okay, and we want to classify each defective item by the type of defect. Okay, and we're going to put that in columns. And we're going to classify in terms of which shift it was produced in. And there are 3 shifts, and we'll use rows to do that. Okay, so we pick 309 furniture defects, and the defects were classified as one of 4 types. So defect A, defect type B, defect type C, or defect type D. And at the same time, each piece of furniture was identified according to the production shift in which it was manufactured, whether it was manufactured in the first shift, in the second shift, or in the third shift. So here's a summary of this information. This is an example of a contingency table. Now the contingency tables that we're going to use are going to have a little more information than this, but this is really all we actually need to perform the test of independence. So let's look at this number 34. What does that number mean? That number means that of all the defects that we've looked at, 34 of them were manufactured in shift 2 having type C defect. The number 17 here means that another way to look at it is, of all the type B defects, 17 of them were manufactured in shift 3. Okay, now we could of course add the rows and add the columns, so we could have row totals. So these three numbers are the totals for the 3 rows. So 15 plus 21 plus 45 plus 13 is 94. And 26 plus 31 plus 34 plus 5 is 96, etc. And at the bottom here we have column totals. So this number 74 is the total type A defects. So if we add these three numbers, we get 74. In other words, there are 74 type A defects of all the 3 shifts combined. And of course, this very last number on the bottom right corner is 309. That just says that we've looked at 309 items. Now another thing we want to put in our contingency table, now these are all observed values, right? Another thing we want to do is we want to put our expected counts for each cell, okay? So what is a cell? This is a cell that contains the counts for type A defects in shift 1. Now when we talk about cells, since we have 12 of them, we want to talk about these cells in an organized fashion. And so what we do is we want to write the position of these cells in an appropriate way. And the way we do that is we look at the row number and the column number. So this one will be in position 1, 1. This is position 1, 2. This is in position 1, 3. This is in position 1, 4. Okay? So when we write the positions, we want to specify the row position and then the column position. For example, this cell is in position 3, 2 because it's in the 3rd row in the 2nd column. Okay? So how do we calculate the expected counts? Well, the expected counts in the ijth position is basically the row total of the cell that we're working in multiplied by the column total of the cell that we're working in divided by the total number of observations, the grand total. So let's take a look at an example. E14. So in other words, I want the expected count in the cell having position 1, 4. That's the 1st row and 4th column. The observed count there is 13. And we want the expected count. So again, we're going to look at the row total, which is in this case 94. So that's here. And we're going to look at the column total. The column total for that column is 38. And divided by, and that's numbers here, and divided by the grand total. And that comes out to 11.56. And what I'd like to do is I'd like to actually put that in the contingency table. Let's do another calculation. So E23, in other words, the expected count in position 2, 3. In other words, in the 2nd row, 3rd column. 2nd row and 3rd column, that gives us the observed count is 34. So to get the expected count, we're going to look at the row total, which is 96, and that's right here, multiplied by the column total. The column total there would be 128 divided by 309, which is the grand total. That comes out to 39.77, and we're going to put that in the table as well. So we're going to take the convention of the counts without parentheses are observed counts, and the counts with parentheses down here are the expected counts. Okay. So here's another calculation. E32, that would be the 3rd row, 2nd column. So that's the observed count. And again, row total times column total divided by grand total. Those are the quantities in this expression here, and it comes out to 26.57. So that number goes there. Okay. So once again, to wrap up here, we have let's just put in all the other expected counts that I've calculated beforehand. And so again, what we're doing is we're taking a defective item and we're classifying it in 2 ways: the shift it was produced in and then the type of defect that was that item has. Okay, now let's look at the question. What are we trying to answer? The question we're trying to answer is the following. Do the data present sufficient evidence to indicate dependence between defect type and manufacturing shift? Okay, so here's that same table again. Our hypothesis, as we mentioned before, is always about independence. So in the null hypothesis, we're going to say that the column variable, which is defect type, and the row variable, which is the manufacturing shift, are independent of one another. And the alternative is the opposite, right? That the defect type and manufacturing shift are dependent. Okay. And since the question has the word dependence in it, that's the original claim is in H1. Okay, now the rejection region. That's going to be a chi-square distribution. And so we have to calculate the degrees of freedom. As I mentioned above, the degrees of freedom is going to be the number of rows minus 1 multiply the number of columns minus 1. So that's 2 times 3, which is 6. So 6 degrees of freedom, 5% significance level gives us 12.59. Okay, so that's our critical value. That's going to separate our rejection region from the fail to reject region. For the test statistic, let's go up here and look at the first cell. In the first cell, the observed count was 15, and the expected count was 22.51. Okay, so we're going to apply the formula observed minus expected squared, that's 15 minus 22.51 squared, divided by the expected count. And we're going to do that for each cell. So for the second cell, it comes out to this expression, and then the last one is this expression, and then if we add them all up, we get 19.1791. So in other words, it's much larger than the critical value, so it's in the rejection region. Okay, the p-value is calculated the standard way. Okay, chi-square greater than the test statistic, and that comes out to a number that's less than 5%. So that validates our decision to reject the null hypothesis. So our conclusion is that there's sufficient evidence to support the claim that the defect type is dependent on the manufacturing shift. Okay. All right, now let's go on and talk about a test of homogeneity. Now, homogeneous or homogeneity means it's a test of sameness, okay? And we're trying to see if a certain characteristic has the same distribution across different populations. And that's, I want to start from this part of the explanation here, because this is a significant difference between the goodness of fit and the test of independence, which deal with samples that come from a single population, to a test of homogeneity where we're talking about analyzing certain characteristic of 2 or more populations. Okay, so so what does it do? We test claims about the distribution of a characteristic for 2 or more populations. So for example, we could look at the distribution of voter sentiment across multiple parties. Okay, the multiple parties here are the multiple populations. Or we could look at the distribution of participation in a physical activity, that's a characteristic, or the distribution of this characteristic, whether or not they participate in a physical activity. And different states, so we take samples from different states, those are our different populations. Okay. In the setup, okay, the null hypothesis is always that this characteristic is homogeneous. In other words, the distribution of a certain characteristic is the same for the different populations that we're working in. And H1 says the opposite, that the distribution of a characteristic differs for the different population. In other words, the characteristic is not homogeneous. Okay. The rejection region is a chi-square, right-tailed, and the degrees of freedom is much like the degrees of freedom for the test of independence. Okay, and no surprise here, the test statistic is going to have the same form. Okay, observed count minus expected count squared divided by the expected count. Now, it's important to understand that in the previous example, our contingency table classifies a subject into categories, or in two methods of categories or classifications. But in a test of homogeneity, what we do is we count a single characteristic for different populations. So for example, a survey of voter sentiment was conducted. So let's take a look at what we got. Random samples of 200 voters were polled in each of the 4 wards. In this case, the 4 wards represent 4 populations, with results shown in the table below. So the characteristic is the opinion of the voter, and the 2 possible answers, or the 2 possible ways we can classify this category, is whether they favor some candidate A or they don't favor candidate A. Okay? But notice that when I'm talking to a subject and asking them the question, I already know which political ward they are from. So I've decided that I'm going to talk to 200 voters for each of the 4 wards. Okay? So over here, this is not a whether they're in Ward 1 or not is not something that's a surprise to me. When I'm talking to these people, I've chosen 200 people from Ward 1 and asking them whether they favor A or not. And what we're trying to see is if the distribution of the opinion across these possible values is the same for the different populations. Okay. All right, so let me get rid of this for a moment and let's just look at this table here. This table now has totals. Okay. What we'd like to do in a test of homogeneity is we'd like to fix the number of subjects that we sample from each party or each population. Okay, so here notice that we've sampled 200 people in each of the 4 wards, and the total is 800 people. Okay. All right, so let's take a look at the expected counts, right? So as before, we'll do cell 1-4, in other words, the first row, 4th column, and the expected count will be, this is the observed count, 48. The expected count will be the row total, which is 236, which is here, times the column total, which is 200, which is here, divided by the grand total, and that's 59. So the observed count is 59. And if I look at 3rd row, or 1st row, 3rd column, something interesting will happen, which shouldn't be a surprise. So this is the observed count for cell 1-3, okay, but the expected count is exactly the same. Well, why is that the case? As a matter of fact, if I calculate all the expected counts in the first row, they will be exactly the same. And why is that? Well, it's because we're working to calculate the expected count under the assumption that the opinion of voters is homogeneous across different populations. Now, of course, we don't have to calculate the expected count of voters that do not favor A, because the total is 200, so 59 favor A, 141 wouldn't. Okay, and of course those are all the same. But as a demonstration, we can calculate E22. The observed count is right here, so the row total is 564 for this cell. The column total is 200 and divided by 800, which is 141. Okay, so let's take a look at the, let's continue this example here. Do the data present sufficient evidence to indicate that the fractions of voters favoring candidate A differ in the 4 wards? So do we have, does the data give enough evidence that the distribution of opinion is not homogeneous across the 4 wards or the 4 populations? Okay. So our null hypothesis is that they are homogeneous. So hypotheses, fraction of voters who favor A is the same in the 4 wards. Okay. Now that's specific to this situation because we can, if we only say that the fraction of voters who favor A is the same, we don't have to say anything about do not favor because of course they are complementary. Sometimes you have your characteristic has more than 2 possible classes, in which case it might be better to use the word distribution of voter opinion is the same in the 4 wards. Okay. And of course, alternative hypothesis is that the fraction of voters who favor A is not the same in the 4 wards. Okay. The rejection region, as mentioned before, is a chi-square right tail. Okay. Now here we have 2 rows, so 2 minus 1 times 4 columns, which is 4 minus 1. So 1 times 3 is 3. And so our chi-square critical value is 7.8. Our test statistic is calculated in the same way as the test of independence. Okay. So this was the observed count for the first cell, 1, 1, minus the expected count squared divided by the expected count. Okay, and this is the computation from the last cell, cell 2, 4. And of course we have this value which is larger than our critical value. In other words, we're going to reject the null hypothesis. Of course, our p-value gives us a little more information of how good the rejection is, and here it's 1%, not too bad. And here is how we write our decision. So our decision is to reject HO so we can support the claim that the fraction of voters who favor candidate A differ in the 4 wards. Okay, so we have a fairly strong indication of a differing fraction of voters who favor candidate A in the 4 wards.